Hello and welcome to my channel. In this math video tutorial, I want to solve this problem on Maclaurin series. And the problem says that we should find the Maclaurin series for the function f of x equal to cos x centered at a equal to 0. So before we start solving this problem, I would love to establish the basics of Maclaurin series by stating the Taylor series. And then if you've not had any basic knowledge about Taylor series, you just check the link to this in the description of this video. You will see the video about Taylor series where I explain the concept and also solve a problem on Taylor series. So but then what exactly is Maclaurin series? Maclaurin series expansion is a Taylor series about a equal to 0, and we know that Taylor series has f of x equal to sigma. This is the sigma notation of Taylor series, and we have it to be x minus a to the power of n, and then we have to this function to the power of n of a all over n factorial. This is Taylor series. So now what is Maclaurin series? We've established that Maclaurin series or Maclaurin series expansion is a Taylor series about a equal to 0. So hence we have the Taylor series to be this. So about a equal to 0, we can get Maclaurin series to be function of x equals, we have the sigma notation of n equal to 0 up to infinity, and then we have x to the power of n, because by the time you plot 0 here, all you have left is x to the power of this n, and then you have f to the power of n. Of course, you represent this 0, this a to 0, or with 0 all over n factorial. So this is what we call the Maclaurin series. All right. Okay, but then if you want to get the expanded form of this Maclaurin series, just like the way we did when we discussed that of Taylor series, it's simple. You just say that f of x is equal to, you start with the power of 0 all over 0 factorial plus, you start with power of 1, continue with power of 1 with the first derivative over 1 factorial. I continue to the power of 2, check the second derivative to 2 factorials plus ellipsis. This ellipsis means that you can continue the third power of x to the third derivative all over 3 factorials, the fourth power of x, the fourth derivative all over 4 factorials, as the case may be. So if you evaluate this expression, of course, from 0 law of indices, anything to the power of 0 is 1. So, and 0 factorial means 1. So if you divide this by 1, you have the first term to be f of 0 plus. We also know that 1 factorial is 1. So if the whole of this divide by 1, so this is what we have, the first derivative, and then plus, we have this one to be just like the way it is. So we just have to rewrite 2 x to the power of 2 second derivative of 0 to 2 factorial. We can as well extend it to the third derivative, sorry, third power of x, and then the third derivative of 0 over 3 factorial, and then plus ellipsis as the case may be. All right, so having gotten the expanded form of the Maclaurin series, then we can solve this problem. The problem says that we should find the Maclaurin series for the function f of x equal to cos x centered at a equal to 0. So we have f of x there equal to cos x. That's where we start with. Since it is given that f of x is equal to cos x, then it means that by the time we substitute 0 for this x, it means anywhere you see x, we could just plot in 0. So we have cos 0, and if you check cos 0, the result would be 1. I think so. Cos 0 should be 1, yeah. Then at this point, you need to check for the first derivative, which is f prime of x. Right, that's the first derivative of this cos. So if you're taking the first derivative of cos, keep in mind that f prime is the same thing as dy over dx. So we are literally saying you should take the derivative of cos x with respect to x. That's what it means. Because in further case, I may not want to do this, but I just need you to know. Maybe when I'm taking the second derivative, which is something like d square x all over d squared y all over dx squared is the same thing. So here, what is the derivative of cos x? And of course, you know it's minus sine x. So if you differentiate cos x, you have minus sine x. Take note of that. So that means by the time we will plot in 0, it means minus sine. In place of this x, we'll substitute 0. And of course, sine 0 is 0. Whether we have a negative sign attached to it, the whole of this process, as much as 0 is multiplying it, the whole of this becomes 0. Right? So we need to check also for the second derivative of x. And that means we need to differentiate this. And differentiation of sine x, we give cos x. Keep in mind that there is a minus sign here. So the second derivative of x, which is the second derivative of this, we give minus cos x. Alright, so at this point, we will need to substitute 0 for x. So that means anywhere we see x, we could represent or replace it with 0. And of course, cos 0 is 1. And here we have minus 1 to be the answer. Alright, let's keep making good progress. At this point, we want to check for the third derivative of x. And that means we should differentiate this. And if you differentiate cos x, that will give you minus sine x. So the minus, we need to affect this minus to change the process to be plus sine x. And then when you plot 0 in place of x, it means that you need to replace this x with 0, and then the result will be 0. Right? So you can actually check for the fourth derivative and also the fifth, as the case may be. In this case, the variation of sine x will be cos x. Right? So the fourth derivative, when you plot in 0 for x, it means you have cos. We have cos x, which is cos 0, which the result will be 1. Alright? You may want to play with it to the fifth derivative, and the result to cos will be minus sine x. And by the time you plot in 0 for x, you have minus sine 0, which will give us 0, right? So let's end it with the sixth derivative of x, and this will give, differentiation of sign is cos, so we have minus, is that correct? Yeah, we should have minus cos x. And then this means that if you plot 0 for x, it means that we'll be having minus cos 0, and this will be minus 1. Alright, so at this point we need to pull the values we have into the formula, the expanded form of this Maclaurin series. So that's the next thing we need to do right now. So we say f of x, keep in mind that f of x, they said, is equal to cos x, and we know that the first value we had for f of x, we are putting everything into this formula. Of course, you know that in the formula we have f of x, the expanded form of it. We have, let's bring it down, the f of 0, this is it. F of 0, we had the value to be 1 here, and we have also f of, that's the first derivative, to be 0. We have the second derivative to be minus 1. So these are the value, we just need to plot this value into here. So coming to this position, we'll have the first one we had to be 1 plus x squared into the second value is, what do we have as second value? That's minus 1. That's minus 1. Okay, for the third value, because the second value is 0, we have the first f of x to be, which is f of 0, to be 1, which we've replaced 1 here. The second one we have is 0, and of course 0 affecting x, the whole of that expression that will become 0. And then the third is minus 1, which we've written. Alright, check, if you check through the formula, this is the first term, this is the first term, this is the second term. This is why I said f of 1, since the first derivative here is 0, 0 times x will be 0, so that has disappeared. This one is minus 1, and that's why we will replace this with minus 1. That's what I'm explaining. Alright, so we have here to be minus 1, and then the next one, remember we have 2 factorials here, plus we have the third derivative to be 0, and because it is 0, this is minus 1, the next one is 0, the whole of that parameter x cube will turn to 0, so we just ignore that. The next one we have is 1, that's for x to the power of 4. X to the power of 4, we have the fourth derivative to be 1, all our 4 factorial. That means the fifth derivative is 0 also. So that means we consider the sixth, which is plus x to the power of 6 into the sixth derivative we have is minus 1. So here is minus 1, right, all over 6 factorial. So this was where we stopped, so we just have to say plus dot dot dot, means you can continue as much as you can. So this means that f of x will be equal to, we have 1, if minus 1 affects this positive sign, we have minus x squared over 2 factorial plus 1 times x to the power of 4 is x to the power of 4 all over 4 factorial, and minus 1 times that positive sign we change to minus x to the power of 6 all over 6 factorial. And this is how you can also check the nature of the formation: minus, plus, minus, and you're having x to the power of 2, x to the power of 4, x to the power of 6. You can even guess the next one to be plus x to the power of 8. Is that true? All over 8 factorial. You can even guess the next one to be minus x to the power of 10 all over 10 factorial. And you can keep going. X to the power of 12 here becomes plus, so plus ellipsis. You can keep going like that. So now we've gotten the expanded series. We can as well represent this in the sigma notation. So in doing that, you can say f of x be equal to, first of all, draw the sigma symbol or notation with the notation or the value n equal to 0 up to infinity. That's the meaning of this ellipsis, meaning that it continues to infinity. And then this is what we want to test run. And now we're having negative, check the nature, negative, positive, negative, positive. That will introduce the function or the fact that we should use minus 1. Because if you use minus 1 to the power of n, say we assume we use n. If we plot in, maybe say the first value 1 here, minus 1 to the power of 1 is still minus 1. And here the first value is positive value. So in order for us to make that real, it means that we have to add plus 2. If you add plus 1, keep in mind that if we choose for first, when n is equal to 1, 1 plus 1 will give us 2, and 2 squared will give us minus 1 squared will give us a positive sign. What if we have our n to be 2 and here is 1? Then it will give us a negative function. But what if we choose this place to be 2, based on the fact that the powers we're having x to the power of 2, x to the power of 4, x to the power of 6, and then we choose our first term to be 1. Do you know that 1 plus 2 will give us 3, and minus 1 to the power of 3 is still minus 1. And then if we have here to be 2, 2 plus 2 will be 4, and this changes to be positive 1. If we have here to be 3, 3 plus this gives us 5. This makes this to be negative 1, and that formation continues. So either ways, it will work for you. Again, checking for the exponent where you have 2, 4, 6, 8, you need to choose x to the power of, if you use n, when you choose the value for the first term, let's say 1, when n is equal to 1, you have x to the power of 1. And we don't have such term here, so you need to use 2 to the power of, x to the power of 2n, because 2 times 1 give us 2. If you choose n to be 2, 2 times 2 will give us 4. If you choose n to be 3, 2 times 3 give us 6. That's why we choose this. And then keep in mind that the numerator will still, this particular power will still be duplicated down here to n factorial. So this is how you want to arrange your work, but to keep it in a more unique way, you want to use something like this: equal to 0, and then start off with minus 1 to n plus 2 and x to the power of 2n all over 2n factorial. Right, so this makes a lot of sense, because if you have minus 1 up to, maybe first term is 1 and here is 1, so you can see that 1 plus 2 will give 3, and then minus 1 to the power of 3 is still minus 1 all over, here is 1 all over 2, because we have 2 factorial. When you choose this term to be 2, 2 plus 2 is 4, and this will change to 1 over, that becomes 4 factorial. So it makes the whole of this to work appropriately. So that's all from me to you. I hope this is helpful to you, or you found it helpful. Please make sure you hit the subscribe button, turn on the notification bell, and like this video. Thank you for watching.